Ted Feitz and Cyntelle Renteria, and our project presentation is on gas detection for the summer IoT boot camp. Basically, our overview starts with our basic purpose, which is to establish a cost-effective and portable noxious gas detection mechanism for two major organizations, the City of Albuquerque and Fuse Makerspace. Our primary focus was the detection and data analysis of airborne pollutants that are emitted from target equipment. And speaking of the target equipment, for the City of Albuquerque, we focused on older diesel buses and other commonly types of motorized equipment that the city might use, but also more modern buses such as the compressed natural gas buses as well. And meanwhile, at Fuse, our target was the fuse floor welding area. And so how did we come up with the pollutant selection? Basically, the final selection was based on two simple criteria: gases that were common to both organizations and the availability of getting sensors for analyzing the gases, which we were greatly helped with from Brian Raship. Although I did also include one of our own sensors that we researched. And we focused on four major gases: carbon monoxide, carbon dioxide, ozone, and particulate matter of 2.5 microns as opposed to larger microns. So at the Fuse Makerspace, basically, as I said before, the gas selection was based more on straight recommendations from Brian Raship and using his experience from the previous boot camp for his gas testing analysis. As far as the City of Albuquerque, as far as their selection, we kept in mind that their gas selection is often sourced from the National Ambient Air Quality Standards. And the NAAQS is basically selects their gases which are focused on causing major threats to human health. That's their focus, and not necessarily greenhouse gases. And they include carbon monoxide, lead, nitrogen dioxide, ozone, sulfur dioxide, and various types of particulate matter. So just a quick table here that just overviews some of our selected sensors that we ended up using for our project. The CO2 was an MG811 sensor. The ozone was an MQ131. The carbon monoxide was an MQ9. And the particulate 2.5 microns was the HM3301. And you can see that three out of the four have the same I2C interface using just a 4-wire combination that we could essentially slave one device to another effectively and efficiently. And the MG811 is a straight analog interface. You can see that the ranges in parts per mil vary from a large range, the largest range for the carbon dioxide, which according to the sensor data sheets ranges from 0 to 10,000 ppm. And then the other ones range from 10 to 1,000 ppm. And then the particulate matter ranges from 0 to 1,000, not what is on the table there. As far as the applications, we thought that was important just to spell that out a little bit. So for example, the carbon dioxide could be used as an indoor or outdoor air quality sensor. The ozone was considered an indoor portable detection device. The carbon monoxide is a typical gas leak detectant or portable gas detectant. And the particulate matter came under a variety because it was a little more robust. It could be used in dust and smoke emission applications, indoor air quality, and industrial particulate matter analysis. And now Cyntelle will talk a little bit about the design and the pictures of the breadboard.
Yeah, I can tell you guys a little bit about the components that we used. for our project. They're all extremely cost effective, and they prove to be pretty durable during our testing. The image on the left is our preliminary circuit design, and the image on the right is the corresponding breadboard layout that we used during our first few testing sessions. We have the particle argon microcontroller, which was great to use because of the Wi-Fi connectivity. We have the 4 sensors that Ted mentioned in the previous slide. The 3 I2C sensors are all wired on the same bus. We also have that single analog sensor. And then we have a NeoPixel ring that basically just visualizes the gas concentration levels of each sensor. The OLED screen displays the NeoPixel color key and describes like a qualitative air quality analysis. And if you click on the button, it changes the OLED screen, and you can see each gas sensor's current readings with a timestamp. And then every minute or so, the data is published to the Adafruit IO dashboard to save the data to the cloud. And so on to the next. Oh, I guess another thing to mention, we ended up having to add an external power supply and sort of wire all of our I2C sensors on one rail, or power them on one rail, and then the rest of the components were powered through the argon. But we'll get into that a little bit later. So next slide. All right. And so I guess just more on the I2C gas sensors. I thought I would show a little segment of our code to show how we collect the data from the I2C sensors. Each of them have their own memory address that we're able to access to extract raw data from. And in order to extract it, we had to perform a read of like 2 separate bytes and then do some bit shifting in order to combine the data into a value that we would then use for calibration and conversion into parts per million. And that's the unit measurement that most of these sensors are built to detect. The data sheets that came with these sensors are pretty sparse, and the charts that they gave you to work with were a little difficult to read. So it took some serious internet digging to figure out how to work with these sensors. And so that concludes that section. What we're now going to do is take a quick video break to show some of our gas detection test sessions. I have just posted a link into the chat. And if everyone, while they're watching the video, if you can just mute your microphones, turn off your cameras, watch the video, and then when you return, if you could just turn back on your video so that we know you finished. All right, hope you guys enjoy it.
What? Okay. Thank you, Ben. I appreciate it.
I think you have to press start back up.
Okay, so if everybody can hear me, we're back from the video. That was a summary of the 8 different sessions that took place over the last week that we've been doing gas collection. In addition to individual mini tests that we would conduct on various sensors to try to get them correctly calibrated. But that's an overview of all the sessions that we took. And here we have a table that tries to summarize by session the issues that were encountered and the readings that were taken in a high level. So you can see our dates, basically it was the span from starting on the 3rd all the way up till yesterday, ranging from anywhere as long as 15 minutes from the tailpipe session that we took up to 2 hours out at the Alvarado bus terminal and at the Pino City maintenance yard. In the middle of the table, you'll see the issues that were encountered, again, at a high level. And you can see we had a number of problems that were encountered over this period of week, this last week. Starting at the top on the 3rd, we encountered calibration and PPM calculation problems with carbon monoxide, carbon dioxide, and ozone. And Cyntelle alluded to the fact that the data sheets were difficult to work with, and there were a lot of incorrect and omitted information that led to those kinds of problems, which we did, with the help of our instructor, Brian, overcome eventually. And then we move toward the, from left to right, we have power, Wi-Fi, and circuit and wiring issues that after we figured out how to calibrate and do the calculations, we encountered these at the maintenance yards and in the welding zone at Fuse and at the Alvarado bus terminal. Power in this case meant power issues related to powering the gas sensors in addition to the breadboard components. So 3 instances there. We had 3 instances where that was also related to Wi-Fi connection to get broadcasting information to the dashboards at the Alvarado bus terminal and the Pino City yard, as well as the Fuse welding zone. So we missed opportunities to broadcast that information to the dashboard. There was also suspect circuit and wiring issues that were encountered when we were developing the case sensor from sort of the breadboard on a stick that you saw earlier in the demo video. And also finally, we had issues with the environment. in 3 instances during our sessions where it was either too cold or too windy, particularly at the Pino maintenance yard when the cold front moved in on Tuesday. And finally, you'll see on the right-hand side, there are 2 columns for valid and invalid readings. And the best way to describe that is during our sessions, we encountered valid and invalid readings for both types of gases, making it difficult to determine which were valid readings and which were not valid readings. And these happened at the welding zone, also at the maintenance yard and the bus terminal. You'll notice on September 4th, we had an additional sensor that was purchased by me that we dropped from the project because it was so problematic related to voltage problems and other problems that we just had to drop it. And this is our final gas detection case design. Basically, at the top panel, you have the 4 gas sensors, and at the bottom, you have the breadboard components with some exposed slits to allow gas to go through and be detected by the sensors. Our conclusions, well, we just picked 5 major conclusions. There were certainly more to come by. Number 1 is don't assume the data sheets are correct. The corrections that were required for calibration and ppm calculations allowed us to finally get valid readings for carbon monoxide, carbon dioxide, and ozone. A second conclusion is that there is background gas present at the fuse floor. So while we were conducting our sessions, we detected high readings of carbon dioxide and ppm 2.5 during the longer welding session breaks, where these persistent high readings did suggest that there could be floor ventilation issues in warmer weather. Another conclusion is that faulty readings were due to erratic power supply, as we already mentioned, but we discovered that separating power sources between the sensors and the remaining breadboard components definitely improved the operational stability and gave us more consistently valid readings. Our initial configuration of a single battery-powered supply was not adequate to maintain proper power to the sensors, and they would just stop working. Another conclusion is that faulty readings were also due to adverse sensor exposure. Sometimes this was pointed out in the data sheets, and sometimes it wasn't. Our sensors basically were not really robust enough to get valid readings in inclement weather, where it was too cold or too windy, with the possible exception of the particulate matter sensor, which works completely differently than the other 3 electrochemical sensors. And finally, we did sustain some microcontroller damage that occurred during the collection process when I stunned the argon because I got it too close to the hot exhaust tailpipe that was illustrated in the demo. So the advice there is to be vigilant and to avoid accidental damage to breadboard equipment while you're trying to collect gases. And one more other point I just wanted to mention was you have to basically, in order to work through all these levels of problems that we had, and we're still working through them all the way up till yesterday, we had to work very closely with our instructor to systematically try to find solutions for these problems, one problem at a time. And this would be also more of a problem in the future when other gas sensors are attempted to be used for the IoT class that are not strictly from Brian's collection. And Cyntelle will give us the acknowledgements.
All right, yeah, I just wanted to take this time to thank our instructors, Brian and Cecilia, for all their support during all this, and as well as the Fuse Makerspace employees for training us on the equipment and helping out with our project. And if you want to hear anything more about the project, you can check out our Hackster. The link is provided below. And yeah, if you have any questions at this time, just let us know.